5 in the first lecture, the lecture on probability theory, a quick review. And in this segment, we're going to talk about random variables. So let's motivate the notion of random variables. We've worked with events so far. The issue with events is that they're not numeric quantities. Events are subsets of a sample space. Oftentimes we are interested in quantities. For example, in the context of analyzing algorithms, randomized algorithms, we are interested in understanding running time, space complexity, message complexity. These are all quantities, and we want to ensure that these quantities have a small upper bound. And so how do we achieve that using events is the question. To do this, all we have to do is to map the events to values, to quantitative values. And that's exactly what is achieved by the notion of random variables. So let's look at the definition of a random variable. A random variable, x, on a sample space omega, is a function, and this function maps omega to real values. And in particular, we will focus on discrete random variables, where the sample space elements will be mapped onto either a finite or countably infinite set of values. So now, every time an event occurs, the random variable x will take on a certain quantitative value, and we can use this to do quantitative analysis. As an example, consider the context of analyzing a randomized algorithm, and we're interested in bounding the running time of this algorithm. And the running time of this algorithm depends on the execution of the algorithm. For the same input, because there are random choices made by the algorithm, it could execute in different ways, in different attempts. And so each possible execution of the algorithm can be thought of as an event, and the set of all possible executions is the sample space. And for each execution, the number of operations performed by that execution is the random variable t. And the goal in randomized algorithms analysis, at least, is to gain a good understanding of this particular random variable t. So random variables can take a wide range of values. Going back to our example on analyzing the running time of a randomized algorithm, a particular algorithm on a particular input could possibly take a wide range of running times based on the outcomes of random choices made by the algorithm. However, we are often interested in understanding the average running time. What happens on average? And to gain an understanding of what happens on average is that we need to use the notion of expectation. So let's say x is a random variable. The expectation of x is given by the weighted average. It's summation overall I, where I ranges over the values that x can take. I times the probability that x actually takes the value I. So this summation gives us an understanding of the average value that x will take. So here's a quick exercise for you. Suppose we have a k-sided die with numbers 1 through k on the die's face. Now, let x be the random variable that denotes the number that appears when we roll a die. Okay. Question is, what is the expectation of x? So, simple application of this formula that we have here, but would be helpful in getting you used to the notion of expectation. Now, there's a very fundamental and very useful property of expectation called the linearity of expectation. Now, let's suppose we have a finite collection of random variables x1 through xn, and each of them has a finite expectation. Now, the expectation of the sum of the random variables is, as it turns out, is equal to the sum overall I, the expectation of the individual random variables. This is a very useful property and it's called a linearity of expectation, and there are some variations to it. We also, let's say x is a random variable, and let's say a is any scalar value. So we also know that E of a times x is equal to a times E of x. This is the main form of this linearity of expectation. And so let's try to prove this form. Let's focus on proving this particular form where there are just two random variables, x and y. We want to prove that E of x plus y equals E of x plus E of y. So let's start with the left-hand side, E of x plus y. And x plus y itself is a random variable. And therefore, what are the possible values that x plus y can take? It can take all forms I plus j, where I is all the values that x can take and j is all the values y can take. And for each of these I plus j values, what is the probability that the random variable x plus y will actually take the value I plus j? Well, it's the probability that x individually takes I and y individually takes j. These are two events, and when we want both of these events to occur, then we'll have to take the intersection of these two events. Okay, so let's proceed and let's expand this expression out, and we will so what we are going to do now is separate the I plus j term into a term with I and a term with j in it. And notice that these two summations, summation over I, summation over j, can be interchanged. So in the first term, we simply take the I out of the summation over j. The term inside the summation over j stays the same. Here we actually notice that we interchange I and j, but that's okay because these are two summations that can be interchanged. We get the term, the j outside of the summation over I, and we have the probability term inside. Okay. Now here's something that is interesting. Let's look at this particular expression to understand what's going on. This is a summation over several j values that these are values that y can take. And inside of this summation, the event x equal to I is unchanged. And this event x equal to I is intersected with the events y equal to j for various values of j. And so and y equal to j for various values of j are all disjoint because y can only take one of them at any time. And so we can apply the law of total probability. And if we apply the law of total probability, this whole term simply becomes the probability of x equal to I. And in similar fashion, this whole term becomes the probability that x equals, sorry, y equals j. So by applying the law of total probability. So now what do we get? Summation over I. Let's look at this term now. This is summation over I times the probability that x equal to I, that's nothing but E of x. And here we have summation over j times the probability that y equals j, and that's nothing but E of y, and which is exactly what we wanted. Now we can extend this proof to more number of random variables just by using induction. So that brings us to the end of our discussion on random variables.